Chapter 1, Vector Spaces, and Section 1.1 Preview. The origin and the fundamental topic of linear algebra is the solution of systems of linear equations in the form a11x1 plus a12x2 plus all the way up to a1q times xq equals b1, and then another equation a21 times x1 plus a22 times x2 all the way up to a2q times xq equals b2, and we can continue with these equations up to, say, ap1 times x1 plus ap2 times x2 plus all the way up to apq times xq equals bp. Here aij and bi are given numbers, either real or complex. Mostly we use real numbers, but sometimes complex numbers. And the indices I can vary from 1 to p, that's the number of equations, and j vary from 1 to q. This is the number of unknowns. So we are looking for the solutions, unknown variables xj. J goes from 1 to q. And this system of equations is equivalent to the matrix equation ax equals b, where a is this matrix of the coefficients, the a's. X is a column vector with components x1 all the way up to xq, and b is a column vector from b1 all the way up to bp. Note the difference between the p and q. The matrix A is called a coefficient matrix, or sometimes it's called a system matrix, and the vector B is called the right-hand side vector, since it's usually written on the right-hand side of the equation. Matrices are denoted by uppercase, usually vectors with lowercase, bold letters mostly in the book, or using vector notation. In my notes I prefer vector notation because it's easier to distinguish from other notations. Instead of using bold letters, I prefer the vector notation. aij is the ij entry of the matrix in the intersection of the ith row and the jth column. And nowadays systems of linear equations are used all the time in sciences, engineering. For example, there is a so-called system engineering. It's also used in finance and economics. In economics, for example, linear programming is a very popular topic. The idea is that nonlinear equations are usually too hard to deal with, and linear equations are quite easy compared to nonlinear ones. The history of linear equations is that World War II and later electronic computers made it not just important but also possible to solve large linear systems. But in fact, the solution method, which we call now Gauss elimination, and which is named after Carl Friedrich Gauss, who lived in the 18th and the 19th century, the 1800s and the 1700s. So we have the basic solution method named after Gauss, but actually already Chinese mathematicians in 179 knew how to solve linear systems. So in general, we have this A system matrix and B right-hand side vector. The basic questions in linear algebra are that when does there exist at least one solution, X? When does there exist at most one solution, X? How to calculate the solutions when they exist, and how to find approximate solutions faster and better. Section 1.2, the abstract definition of a vector space. So definitions are usually abstract in mathematics, and there are a lot of abstract theories related to linear algebra in different areas of mathematics. But this course is mostly an introductory course with computational applied linear algebra topics. For example, Cartesian coordinates are introduced in middle school and vector addition in high school. And there are a lot of properties of vectors and vector spaces. In mathematics, what we try to do is we restrict the defining properties as small as possible, as few as possible, and then the rest of the properties are proven from the previously established defining properties. So here is the main definition. A vector space V over the real numbers is a non-empty collection of objects called vectors, together with an operation called vector addition, which assigns a new vector u plus v, which is in V, to every pair of vectors u in V from V. And also there is another operation called scalar multiplication, which assigns a vector alpha v in V to every real number alpha and every vector v. And once we have these two operations, the vector addition and scalar multiplication, we also assume that these operations have the following properties. Property 1, for every pair of vectors uv, u plus v is the same as v plus u, which means the vector addition is commutative, you can change the order. Then if we have three vectors u, v, and w, the addition is binary operation, so when you write down three vectors u, v, and w, if you want to add them all together, by the definition of addition, you have to pair them. So once you have, for example, v plus w, that's a new vector, and then you can form this binary operation, another plus, with u to get a new vector. But it turns out that it doesn't matter how you pair these vectors, the addition remains the same, the result of the addition. So u plus v plus w is the same as u plus v plus w. And we call this the associative property of addition. Property 3 is that there is a zero vector, which is also called the additive identity. This is usually denoted with zero vector notation. And the property of the zero vector is that 0 plus v equals v plus 0 equals v for every vector v. That means when you add to any vector, it doesn't matter in what order, it doesn't change the vector v. Property 4 is that for every vector v there is another vector w such that v plus w is 0, and this w vector is called the additive inverse of v. Property 5, for every vector v, 1 times v is v, where 1 is the identity from the scalars, the multiplicative identity from the scalars. For the property 6 is that for every pair of real numbers alpha and beta, and for every vector v, alpha times beta times v is the same as beta times alpha times v. And this is called the distributive property. So here the idea is that the scalar multiplication is a binary operation. That means when you do it, you have to do it in pairs, one real number and one vector. So if you have two real numbers, somehow you have to pair these. You can either pair with beta and v, and then you get a new vector, and then you can scalar multiply this with alpha, or you can pair beta and alpha together to get a new real number and then do the scalar multiplication. Property 7 is that for every pair of real numbers alpha and beta and every vector v, alpha plus b times v is alpha times v plus beta times v. This is also called the distributive property like the previous one, but this is the distributive property with respect to scalar addition. So when you add together two scalars, you can multiply this term by term with the vector v. While the previous distributive property was for scalar multiplication. Property 8, for every real number alpha and every pair of vectors u and v, alpha times u plus v equals to alpha times u plus alpha times v. This is again called distributive property, but this is now with respect to the vector addition. So we are distributing scalar multiplication through vector addition, term by term. So these are the 8 properties, and sometimes actually the definition of this addition and scalar multiplication also added to these properties as first two properties, that this is in V and the scalar multiplication is in V. And then we would have altogether 10 properties. But separating these definition of the addition and multiplication, we have 8 additional properties for the vector space. So some remarks in item 2, because it doesn't matter how we pair them, then we might as well just leave out the parentheses, brackets, and just write u plus v plus w, since it doesn't matter what order and how we pair these. Then in item 6, similar thing, that it doesn't matter how we pair these things. That means that we might as well just leave out the parentheses and write alpha times beta, beta times v. So throughout the semester, we will use the notation boldface uppercase R for real numbers, boldface uppercase C for complex numbers, and then we will also often use the boldface uppercase F in those cases when it doesn't matter whether we use real or complex numbers. Then we just use F, and that can denote either of or both R and C. So together all these numbers, the real numbers, complex numbers, or general numbers from F, these are called scalars usually. And by the way, F really stands for a field that's usually discussed in abstract algebra. If you go back to the definition of the vector space, we used real numbers here. So the way we say is that the above definition of vector space is over the real numbers, R. Alternatively, we can also define the same way the real vector space over the complex numbers instead of the real numbers. So the main lemma of this section is lemma 2. It says that if V is a vector space over F, that means it doesn't matter whether you consider real or complex numbers, then we have these additional properties. So again, the idea is that these are, if you think about vectors that you learned in middle school or in high school, those vectors have this property, but the idea is that we list only the basic ones in the definition, and then we derive all additional one as a lemma. So we prove all this. So these properties, the first property is V has exactly one zero vector. Yeah? So if you go back, defining property 3 was that there is a zero vector. It doesn't say that exactly one zero vector, but actually we can prove that you cannot have more than one. Then property 2, every vector u has exactly one additive inverse, which means that if you have a 2 v and w such that u plus v is 0 and u plus w is 0, then actually v equals w. Property 3, for all v vector, if you multiply with the 0 scalar, this v vector, you get 0 vector. It's interesting again to go back and see that this wasn't mentioned anywhere here. What we have is, actually we don't mention the scalar 0 anywhere. We have a vector 0, 0 vector. This one mentions now the 0 scalar. Then property 4 is that for all alpha scalar, we have that if you multiply the alpha scalar with the 0 vector, we get the 0 vector. Then kind of the opposite of this, we have that if alpha is a scalar and alpha times v is 0 vector, for some non-zero vector v, then what we get is that alpha must be 0. Property 6, vector -1 from the field, the -1 times the vector v, is the one and only additive inverse of v. Again, let's go back to the definition and check what it says about the additive inverse. Well, the definition just says that there must be an additive inverse such that v plus w is 0. But it doesn't say that it must be 1 or 2 or how many additive inverses can exist. And also, this says that the way we get the additive inverse is that we just multiply the original vector with the scalar number -1. And property 7, if alpha and beta are scalars and alpha times v equals to beta times v for some non-zero vector v, then alpha must be equal to beta. So let's prove a few of these. The first one, that they're exactly one zero vector. So if we have a zero vector and then we have another 0 tilde vector that are both playing the role of zero vectors, then by item 3 of the definition says that we can add these zero vectors to other vectors and it doesn't change those vectors. So the trick is now that if you start with the zero vector, we can add to this the 0 tilde vector, and it's the same because the 0 tilde is a zero vector, but then the zero vector is a basic zero vector, so that means that it doesn't change the 0 tilde. So that equals to 0 tilde, and then comparing the beginning and the end of this equation, we get that the two zero vectors must be the same. Proving the second one, that says that there is exactly one additive inverse. So let's assume that there are v and w inverses of u. Then we can write v as v plus 0 using the third property of the definition that says that we have this zero vector that can be added arbitrarily to vectors and it doesn't change. Then property 4 says that the zero vector, it can be obtained from the additive inverses. So if w is an additive inverse of u, then u plus w equals to the zero vector according to property 4. Then the property 2 of the definition says that it doesn't matter how we group these three vectors. So we might as well change the parentheses to v and u. Then once we have v and u, checking again what was v and what was u. So v is additive inverse of u. That means v and u is 0, v plus u is 0. So we get that this is 0 plus w. And then again, using the definition 3 property, if we add 0 to any vector, that doesn't change the vector, so that means u plus w is w. And again, comparing where we started and where we ended, we get, just using the properties of this vector space, we get that v must be equal to w, so you can only have one additive inverse. Property 3, it says that scalar 0 times v is the zero vector. So we have this vector v, and then the 0 times v vector. Let's denote its additive inverse by w, which means that 0 times v plus w equals to the zero vector. Then starting with the 0 times v vector, we use the definition of 3 part, which says that we can add 0 to this and it doesn't change. Then we can use the definition of w, that it's additive inverse, which means 0 can be written as 0 times v plus w. So we replace the 0 vector with 0 times v plus w. Then we have these two terms with the zero scalar in them. So now we use definition part 7 that says that we can factor out the vector from two terms. So if we factor out v, we get 0 plus 0 times v plus w. Then here we assume that we know that this 0 is in the scalar field, real number or complex number 0, and we know for those numbers that when you add 0 to 0, it doesn't change, so you get 0. 0 plus 0 is 0 for scalars, for sure. So we get 0 times v plus w, but then the definition of the w is that it's the additive inverse of 0 times v, which means this is the 0 vector. Starting with 0 times v, we obtain that this is the 0 vector, and that's what property 3 was. Property 4, showing that alpha times the 0 vector is 0 vector. So it's very similar to this previous one, but now we denote by w the additive inverse of alpha times the 0 vector, which means that alpha times 0 vector plus w is the 0 vector. And again, we start with alpha times the 0 vector. Again, we add the 0 vector to that because it doesn't change anything, adding 0 vector. Then we use the definition of w, and we replace the 0 vector with alpha times 0 vector plus w vector. Then we use from the definition property 8 that says that from vector addition we can factor out common scalars. So here we factor out alpha and you get 0 vector plus 0 vector, and that shouldn't be there, this v. So after we factor out alpha, we get 0 vector plus 0 vector plus w vector. Now the 0 vector has this property again that it doesn't change when you add to any other vector, so this is alpha times the 0 vector plus the w, but then this equals to the 0 vector according to the definition of w. Again, comparing this 0 vector to where we started, this equals to alpha times the 0 vector, and this is exactly what we had to show. Property 5. So this is now saying that if alpha is a scalar and alpha times v is the 0 vector for some non-zero vector v, then alpha must be equal to 0. So let's first of all write this as an if-then statement. And the if part has two parts. So we have that alpha times v is 0, and also we have this for non-zero vector v, so that means v is not 0. And then this implies that the alpha scalar must be 0. So this is an implication that we want to show is true. One way to show an implication is that we use the contrapositive, and the contrapositive of an implication P implies Q is not Q implies not P. And you have to know that the contrapositive is equivalent to the original implication. So the two are equivalent. Writing down the contrapositive of this statement, then we have to negate alpha equals 0, that's alpha is not 0, and then this is supposed to imply the negation of this AND statement, which is an OR statement with the negation of this equality and inequality. So that means we get that alpha times v is not 0 or v equals to 0. And then we prove this in the following way. Assume that alpha is not 0 and a times v equals to 0. That means this is false. So that means this whole thing must be true, but then that means that v must be equal to 0. So this is the plan, that we use the contrapositive in this special form, that from this implication we assume that alpha is not 0, but we know that alpha times v is 0. And then we check what happens with v. From property number 5 of the definition, we have v can be written as 1 times v. And then since alpha is not zero and it's a scalar in F, it has a reciprocal. We're supposed to know that from, I don't know, elementary algebra, that a number, scalar number, has a reciprocal. We can write this as alpha to the negative 1 times alpha, and the product equals to 1. And then definition property 6 says that we can distribute this scalar multiplication. So that means that we can write alpha inverse alpha, which is 1, times v, as alpha inverse times alpha v. Now, according to our assumption, alpha times v is 0. And then what we have from step number 4, the previous step, is that alpha inverse 0 is 0 vector. We already shown that. So we get that v equals to the 0 vector, which means that this implication is true. And this is the contrapositive of the original implication, which is then proven to be true. Items 6 and 7 will be homework assignments. But we mentioned here that the additive inverse minus 1 times v of a vector v is usually denoted by simply minus v. But this is simply a notation. And also correspondingly we write u plus minus v, where minus v is the additive inverse of v. We simply write this as u minus v, like a subtraction. But you should remember that this is, by definition, is adding together u with the additive inverse of v. Some examples. For example, the set of column vectors fp, where we have components x1 through xp, and these xi components are scalars, either real or complex, as I goes from 1 to p. So this can be also called the p vectors, the vector space of p vectors. We define the vector addition by the usual component by component addition. So if you have an x vector x1 through xp and another vector y1 through yp, then we add them together component by component to be x1 plus y1, and the last component xp plus yp. And then the scalar multiplication is also defined component by component. So the alpha times x1 xp vector is alpha x1 and alpha xp vectors. Let me remind you that in the definition of a vector space, it says that we have to have a 0 vector with this property. So in this example, the 0 vector will be the vector with all 0 components. So these are scalar zeros in the components. And this could be also RP, where we have only real numbers, or it could be CP, where we have complex numbers. So the 8 defining properties are included in the definition. It can be checked, actually, if you remember the properties of vector addition. They exactly cover all the 8 properties. Next example, the set of P by Q matrices with entries from the field F. It's a vector space with respect to the rules of entry by entry addition and entry by entry multiplication by a scalar. We will work with matrices a lot, and we will practice this later, how to add them, scalar multiply them. We can also have some very, very abstract vector spaces defined. For example, let's use for V the 3 to infinity interval. So this is the open interval with numbers larger than 3. Then if you have UV vectors from this space and the alpha real number, let's define the vector addition as U box plus V equals to U times V minus 3 times U plus V plus 12. And we also define the multiplication by scalars as A times box dot U, which is U minus 3 to the A plus 3. So the important thing is that the addition, this is a very abstract vector space, And the addition is box plus, and the scalar multiplication is box dot. On the left-hand side, we have the abstract operations defined. On the right-hand side, these are all classical, traditional operations. So this is u times v, this is just regular multiplication. And actually the vectors are really numbers, since this 3 infinity interval is a subset of the real numbers. So in fact we have numbers, real numbers here. And for them we have multiplication, addition, and so on. All the basic operations. Same thing here with the dot, box dot, scalar multiplication. This is defined in terms of the traditional operation, difference of two numbers. This is the power of numbers, and adding two numbers. So this can be and should be checked that the 8 defining properties hold for this operation and this vector space. And that's why it's actually a vector space. And we also have to check, and we're supposed to check that if you add together two of the vectors, this is also in the vector space, so it's close to vector addition. That means if you add together using this special operation, two vectors, you get a vector which is larger than 3. And the same thing with the scalar multiplication, that's supposed to be box dot. We're supposed to also check that this is inside this set, 3 infinity interval. So let's see some particular examples of this special addition. 4 box plus 5 is, you multiply together 4 and 5, minus 3 times 4 plus 5 plus 12. So that's 4 times 5 is 20. So these are now traditional operations. 4 times 5 is 20, minus 3 times 9 is 27, plus 12, that's altogether 5. And you can see that this is in fact really in the set because it's larger than 3. Then minus 5, box dot 7. By definition, the way we calculate this is that 7, the vector, minus 3 to the minus 5 power, plus 3. And this is then 3 plus 4 to the negative 5. 4 to the negative 5 is a positive number. Add it to 3, that will be larger than 3. Then, for example, if we denote the additive inverse of u with box minus u, then if you want to calculate this additive inverse, box minus u, we have to use the defining equation that u box plus this additive inverse box minus u supposed to be equal to the 0 vector. But that means that first we have to determine what the 0 vector is. Because we have very special operations, it doesn't say that the 0 vector must be the 0 number. Actually, it turns out that it's not. So if you go back here, nowhere we say in the definition that the 0 vector is simply the 0 number. For this previous example, we had that the 0 vector is actually the 0 of the vector of the 0 scalars. But here, if we have to find a 0 vector, then the definition of that is that the 0 vector added to any vector with this box plus, it doesn't change the vector, so it equals to u. Now if you write out what this box plus means, we get an equation that says that 0 times the u times the 0 vector minus 3 times u plus 0 plus 12 equals to u. And here we have an equation with the traditional operations, and this equation can be solved for u. I'm sorry, for the 0 vector. So we solve for the 0 vector, we can multiply term by term. We can rearrange. What we get is that u minus 3 times 0 vector equals u plus 3u minus 12. And then we can divide through by u minus 3 to get that 0 equals to this 4 times u minus 3 over u minus 3. And after simplification, we get that this is 4. So what we got is that the 0 vector is actually the number 4, which is great because what we see is that the 0 vector is also in the space V, which is the interval 3 to infinity. By the way, that the 0 vector is supposed to be in the interval 3 infinity. That means that it's impossible to have the 0 scalar as the 0 vector. Again, the idea is that using this special, very special box addition, if you add 4 to any vector, it turns out that it doesn't change, and you get back the original vector u. So once we have the 0 vector, we can calculate the additive inverse in general from this equation that u box plus box minus u supposed to be equal to the 0 vector. Again, the idea is that we write out these operations and we substitute what the 0 vector is. It's 4. And then we can solve this for box minus by using standard basic algebra. So we multiply out, factor out things, and what we get is that the additive inverse of u under this special box plus operation is this box minus u vector, which is simply 3u minus 8 over u minus 3. By the way, this additive inverse is supposed to be also in this set V, which is the interval 3 to infinity. So one would also have to check that this is really larger than 3. Let's not do that. It's a simple manipulation of fractions. The idea is that then if any of the defining properties fail, then we don't have a vector space. So one definition or one example for that is if you have a space R2, it's not a vector space when we choose the addition as taking the maximum of the corresponding components. So if we have u vector with u1, u2 components and a v vector with components v1, v2, then the addition u box v is the maximum of u1 and v1 and the maximum of u2 and v2. The scalar multiplication, let's leave it as a usual entry by entry scalar multiplication. One can check several things that fail from the 8 properties. One is enough. If one fails, for example, we can show that there is no 0 vector. So we're supposed to have a 0 vector in a vector space, 0, and then add it to any other vector. It's supposed to be just the vector itself. So if we assume that we have a 0 vector with components z1 and z2, then we're supposed to have that u box v vector is just the u vector. Writing out the definition of this box operation, we have that maximum of u1 and z1 supposed to be u1, and the maximum of u2, z2 equals to u2. So we compare vectors component by component. So how it's impossible to have this sometimes. For example, if you choose u, assume that the 0 vector exists with z1 and z2. If you choose u to be the vector with z1 minus 1 and z2 minus 1 components, then if you take this plus box operation, this is supposed to be the maximum of z1 minus 1, z1, and the maximum of z2 minus 1, z2. But when you subtract 1 from z1, that's less than z1. And similarly, the same thing with z2. So z2 is the maximum from the second component, and z1 is the maximum from the first component. But because u was z1 minus 1 and z2 minus 1, clearly this is not the same as z1 and z2. So it's impossible to have a zero vector that works for all u vectors, because, for example, for this special u vector, it fails the defining identity. Another example, let C be the subset of R3 vectors with components a1, a2, a3, such that the polynomial a1 plus a2t plus a3t squared is greater than or equal to 0 for all real number t. Another way to write this down with the set notation is that C is the set of three vectors a1, a2, a3, such that for all t real number, a1 plus a2t plus a3t squared is greater than or equal to 0. So it's not difficult to see that when you add together such vectors, it's closed under addition. It stays non-negative when you add together a1 with b1 and a2 with b2 and a3 with b3. It's also closed under scalar multiplication by positive numbers. So that means that for all a from this set C and alpha positive number, we have that alpha times a is in the same set C. But still, C is not a vector space over the real numbers, because if we multiply with negative number, the inequality changes. So this inequality doesn't hold anymore when you multiply with negative number. That means it is not true that for all alpha real number and for all a vector, alpha times a is in this set C. In fact, the opposite is true. If we negate this statement with these universal quantifiers, then this is equivalent to saying that there is an alpha real number and there is an a vector from C such that alpha times a is not in this set C. That means we need to find alpha and a vectors such that a is in C. That means a1 plus a2t plus a3t squared is greater than or equal to 0. But when you multiply it with alpha, that means you get alpha times a1 plus alpha times a2t plus alpha times a3t squared. We get less than 0. So then you can guess from here that in order to get this strict inequality after multiplication, we're supposed to start with the strict inequality before. That means a1 plus a2t plus a3t squared should be positive. And in order to flip the inequality, we're supposed to multiply with negative scalar. So for strict inequality, for example, let's choose of a1, a2, a3 to be the vector 1, 0, 1. Because then what we have is that this a1, a2t plus a3t squared is just 1 plus t squared. And this is greater than or equal to 1, which is greater than 0 for all t. And then when we multiply this with alpha negative 1, we get the alpha a vector with components minus 1, 0, minus 1. And then when you calculate the polynomial for this alpha a, we get that this is minus 1 minus t squared, which is less than minus 1, which is less than 0. And that means that alpha times a is not in C. So this is called a counterexample that we found for the original universal statement. Next example, let V be the set of polynomials P of lambda, where P of lambda has the form sum as j goes from 0 to n, a sub j, lambda j, alpha j's are complex numbers from with index j equals to 1 to n. So we can also say that this is a space of polynomials of complex variable lambda with complex coefficient and with degree less than or equal to n. And this is a vector space when you look at the natural addition and scalar multiplication of polynomials, which means term by term addition. In a final example, let C01 denote the set of continuous real-valued function f of x on the interval x greater than or equal to 0, less than or equal to 1. So this 0, 1 closed interval is there in the notation, and C stands now for continuous functions, real-valued. What we have is that C01 is a vector space over R with respect to the natural rules of vector addition. When functions are added, the sum function is evaluated as at x as the sum of the values of f1 and f2 at x. And also the scalar multiplication defined as alpha times f function evaluated at x is just alpha times f of x. So this is it from this first section. We will continue with working with vector spaces.